to the Huon method, we have to use Euler as the predictor. And after that, we have to determine the end slope. We determine the end slope, and after that, we use the end slope and the initial slope to find the average one, the average slope. And after that, we use the average slope for the final solution. Okay, this is the concept of Huon. Okay, so then we will working on that. For Huon, okay, we have the equation of dy by dt, dy by dt equal to yt cubed minus 1.5y. Okay, this is fty. Okay, for Huon, we should create a table. For this case, we should have the time step first, and after that, we will find the initial slope. Okay, initial slope, that is actually, it is what? It is f x I y I. This is the same initial slope. Okay, and then we determine the predictor. Determine the predictor. Predictor is actually a solution of the Euler method. That is y t. Okay, that is yt. Yt at the end slope of the predictor is not the exact one, it's just yt. And after that, when we have yt, we will determine the end slope. Okay. I would like to write it right. yi plus 1. Okay, yi plus 1 t. I use the superscript p as the predictor. Okay, this is the predictor. It's not the exact one. And then we determine the end slope. Okay, end slope is equal to L x. Okay, if we use xi and yi to be x0 instead, that is like the initial value. Okay, and then end slope, it should be x1 and y1. Okay, in order to reduce the information in written in the table. Okay, so we know this is end slope, and after that, we will determine the average one. Average slope. So average slope is come from the average value of initial slope and end slope. Okay, that is sorry for this. This should be t. This come from f t0 y0 plus f t1 y1. Okay, divided by 2. Okay, this is the average one. And then we got the final solution, that is corrector. For this case, I will not use the iterative process to adapt the average slope to adjust the average slope until it is constant. I will not do that. I will do just the one, just only first step. For one, just only one step. This is a corrector that we will got yi plus 1 over here. Okay. That's all. Okay, we may starting with the initial value first. For the case of initial value, when time equal to 0, y equal to 1. Okay, so at this case, this row is not necessary to determine because this is the initial step. Okay, then we will do next. We will solve for one of h equal to 0.5. Okay, so for h is equal to 0.5. We will solve just only one step, just first step only. After that, we will use the Excel to show you how to develop the Excel sheet for calculate this problem by Huan. Okay. So according to this, initial slope is equal to what? Okay, we substitute for initial slope. Initial slope is equal to yi, right? Yi for this case is equal to 1. Multiply with t is equal to 0 cube minus 1.5 y is 1. Okay, this is the initial slope. So it's become what? It's become 1.5. Okay, this become what? 1.5. After that, we use the initial slope for predict the final point. That is, we call the predictor step. That is, we use the Euler method for this is equal to yi plus f ti yi multiplied with h. Okay, so for this case, yi is equal to 1, right? Plus f ti yi we already done. This is equal to 1.5. Okay, multiply with h is equal to 0.5. So what is it? Oh, sorry. It should be negative. After that, what's happened? We will got the solution of one minus 1.5 multiplied with 1.25. The predictor. What's happening? Am I wrong? yi equal to 1 plus fxy. I'm sorry, it should be 0.5. Okay, this becomes 0.25. Okay, so the predictor is become 0.25. Is correct? After that, we use this value. Okay, t equal to 0.5 and y equal to 0.25 to finding the end slope. End slope is become, we have to use this formula, right? This is the end slope. Y is become 0.25. Okay, t equal to 0.5 cube. Okay, minus 1.5 y 0.25. Okay, we use this value as a predictor in order to find the end slope. So it's become, the end slope is minus 0.34375. Okay. After we have the end slope, we use the end slope and initial slope to find the average one. So we got the average slope equal to minus 0.921875. Okay. Then we use the average slope in order to find yi plus 1 in the corrector step. Is equal to yi, that is 1, right? Plus average slope average slope multiply with h. H is 0.5. Okay, h is 0.5. So then, what is it? So we got a solution of okay. Then that's all for the first step of Huan. This is for the first step of Huan. Huan first step. Okay, do the same thing for next step. That is for t equal to 1. Okay, we do the same thing by using next, that is when time equal to 0.5 and this value, we use this row as the initial value and do the same thing, do the same procedure. Okay, right now we will develop the Excel sheet for this case of Huan. Okay, I would like you to focus on the Euler and Huon method, and also the midpoint method. You have to concentrate on this first. After that, when we move to Runge-Kutta method, it should be better. It should be better because it is the same procedure, but it's maybe called in different. For this case we call like initial slope, end slope, or something. But in Runge-Kutta method, we will call as the functional K1, K2, K3 instead. Okay, that actually it is the same. Okay, so let's we move to the Excel sheet for Huon. Okay, this is for the Euler. I will crop the exact solution first. This is the exact one. Okay, so for Huon, we have to determine the initial slope, right? And then we will obtain the predictor. Okay, and after that we use the predictor to determine end slope. Okay, and then we will determine average slope. And after that, finally, we will obtain corrector. Okay, and finally, we can determine the percent error. Initial slope, what is this? I may use like T0, Y0. Okay, predictor is Y plus 1, Y3 plus 1. Okay. And the end slope may be represented by F P plus 1. I may write by this. It may be easy to understand. From 0 to 1, it may be better, right? Okay, so this should be Y1. It should be have more meaning. Y1 subscript P, that it should be predictor. Okay, so the average slope, this is the average of F xy that we have to value, right? And after that, we will plot the corrector that is y1. Okay. If you have any question, you can inform me that. Okay, for the first step, it's not necessary to solve because it is the initial condition that it should be 1, right? So this table is not necessary to solve. And the error should be 0. And then move next. Initial slope is what? Function. For this case, we use A as 1.5. Okay, then what is this? It should be equal to what? Is equal to y, right? Multiply with what? Multiply with t. Ti. Then it should be the previous step also. Power 3. Okay, minus 1.5. A is equal to 1.5 times y. Okay, done. We have the initial slope of this. Okay, and in this case we use h is equal to 0.5. Okay, so predictor is equal to what? Predictor is the Euler, that is yi, right? Plus initial slope multiply with h. Multiply with h. For this case, h is 0.5. Okay, so we obtain here. Actually, if we set up something, h so and y is multiplied with step side. Step side is over here. For this trick is actually is not necessary. And after that, when we have the predictor, we can determine for the end slope. End slope is equal to what? Is equal to yt cube. Y is become here. Okay, multiply with t cube. Okay, minus 1.5 y. We obtain the end slope. Okay, and the average one, average is initial slope plus end slope and divided by 2, which is the average one. Okay, after that, we can determine the corrector. Corrector is yi plus the average slope multiplied with h. Okay, now we have the solution already. The solution is 0.53, but the exact one is 0.479. Okay, so what is the percent error? We have 12% error for this. Okay, after that, do the same thing. We got the solution over here. Okay, because it is working on the step we use the initial step and the initial value, and then we will do next. Okay, this is the initial value, and after that, when we stop, after we finish the next step already, for this case we finished the step of 0.5 already, then the step side, the step of 0.5 become next initial value, and use this value to forecast next value, next time step, the value for next time step. Okay, that's all for Huan method. That's all for Huan. Do you have any question? Okay, so if we change the step size, maybe just 0.5 first. Okay, if I copy first to back up the solution. It's for backup solution. Okay, and then if I change the step size, reduce it to be just 0.1, what happened? If it's become 0.1, so the error is become reduced significantly. Okay, what's happened next? If we set to 2 rate, oh, it's okay, right? If step size is small enough, so what's happened to when y equal to 2? When t equal to 2. Okay, you see that the error is increased as any time that we increase. So actually the Huan method is still not good enough, because it's produced the error increase when the time step is increased. We do not want that. We not need the solution like this. Okay, the error should be in the same order. Okay, for example, if the error of the first iteration is maybe in the order of 0.1%. Okay, so for next time step, the error should be in the same order. That is acceptable. Okay, but for this case, the error is produced. It's growth. The error is growth as the time step is growth. Okay, if we do it again, not stop at time equal to 2. When we move to until here, oh, sorry, it should have the value that is okay, if this time is become here, okay, it should have something on the function, on our function, that it should be based on the exponential form. Okay, so when time is increased until some value that it should be increased enough is maybe reached to the infinity one. Okay, so as we show, as this solution show that when we use Huan method, okay, the error is maybe not higher like the Euler, but the solution is still not good because the error is increased. Okay, so it's just the concept, just only the concept, that is Huan can be used for adjust or adapt the Euler method. Okay, next we will working on the final method, that is the midpoint method. Okay, and the question number D is the percent error for each method we already include in the table already. Okay, so the midpoint, what is the concept of midpoint? Midpoint is what? For the case of midpoint, we have the same thing, but yi plus 1 is determined by yi plus the slope at mid-step, the slope at mid-step. The slope at mid-step multiplied with h. So what is the slope at mid-step? It is f xy, that x I plus h over 2 and yi plus h over 2 instead. Okay, in this case it should be t, right? Okay, and multiply with h. So for the case that we use the midpoint or modify Euler method is for midpoint method or modify Euler method with h equal to 0.5 in the same. Okay, so how can we do? Okay, the table should be, we should have time, right? Okay, time should be starting with 0.5 when we use h is equal to 0.5, same as the one and Euler. And after that, what is it? We have to find initial slope, right? We find initial slope, and this one, f x0 y0. Okay, and then for this case, we require x and y also. We require new x, that is at x equal to xi plus 0.5h. That is the point x at mid-step. I represent it by x1. Okay. After that, in the same, this is yi. Okay. This is at the point we use Euler. We use Euler to solve the value of y at mid-step. Okay, I will call initial slope as k1. Okay, for this case I call initial slope as k1. So for the midpoint, it's become yi plus 0.5 k1h. This is the value at mid-step, value of y at mid-step. I represent it like y1. Okay, after that, we have x1 and y1 from the Euler method that we solve for value of y at mid-step. Okay, then we determine k2. K2 that is represent the slope at midpoint at mid-step. Okay, and this we call f x1 y1. Okay, sorry again, it should be t, right? Okay. After we have the slope at midpoint, and mid-step already, then we find the solution. We obtain the solution that is yi. Okay. So for our problem, okay, when time equal to 0, y equal to 1. This is for the initial value. Okay. This row is not necessary to solve first. It's called initial value. After that, we use this initial value to solve for the initial slope first. And initial slope we already done from previous method. Okay, this is initial slope. Actually, it is the same. Okay, it is the same. Initial slope is equal to minus 1.5. Okay, and then when we would like to solve the position at mid-step and mid-step. So the step size h is equal to 0.5. So at mid-step it should be 0 plus 0.5 multiplied with 0.5. So it's become what? 0.25, right? Okay. After we get t plus 0.5 h already, then we determine for the value of y at mid-step. Value of y at mid-step is what? Is yi. Yi is 1. Okay, plus 0.5 k1. K1 is initial slope. This is initial slope. And then multiply with h. H is equal to 0.5. Okay. Okay. We actually, I may rewrite form of this to be, it should be h over 2. Okay, it's maybe better understand. Okay, and then it's reduced to 0.5 k1s is, it should be okay. This is all right. After that, 1 minus 1.5 times 0.5 over 2. So we obtain the solution of 0.625. Okay, 0.625 over here. After that, we have the solution at mid-step already. Okay, then we do the same thing. Use this value and this value, substitute into y into FTY into FTY. That is FTY is FTY is YP cube minus 1.5y. Okay. So for K2, that is the slope at mid step. So for K2, that is F T1 Y1. Okay. T1 is equal to what? 0.25. Okay. Y1 is equal to 0.625 times T1. So what happened next? So then we get the solution of it is the solution here. Okay, and then for the solution, final solution is what? Yi plus 1 is become yi. Okay, plus slope at midpoint, that is slope at midpoint. This is a slope at midpoint. H. That is what? That is yi is 1, right? Slope at midpoint over here is become minus. And 5 with H is 0.5. So we got the solution of okay. This is the solution. Okay, we understand for the midpoint. After that, we can find the percent error and use this as the initial value to perform the next step, to determine next step. Okay, you understand for midpoint method or modified Euler method. Okay, we will working on the Excel. Okay. Do the same thing as the one. Do the same thing as the one method. But the column should be, this is initial slope, that is correct. Okay. The predictor right now, it should be initial slope, we represent it's like A1. Predictor, now we will not call it predictor anymore. we have to determine not predictor, we have to determine we determine for x at mid step first, that is xi plus 0.5 h. It is the x at mid step. We determine x at mid step and we call like x1. And after that, we determine y at mid step. That is yi plus 0.5 k1h. Okay, we will call y1. Okay, and after that, we will determine for the slope at midpoint that we call it like k2. Okay, and the average slope is not necessary anymore. Okay, and then we will obtain solution. Okay, this is just for the case of midpoint. Okay. Now, how can we start? We set up, it should be 0.5 first. Okay, and initial slope is equal to what? Initial slope is equal to yi, right? Equal to yi time t power 3 minus 1.5 y. Okay, this is initial slope. That's already done. It's already correct. And after that, x plus 0.5 h is equal to what? Actually, on this table, it should be t, right? It should be t plus 0.5 h okay, now we have the solution over here. And then we use the Euler to predict the value of y at mid step. That is equal to yi, okay, plus initial slope, okay, multiply with h, but it should be a half h, so it's become 0.5 h over here. Okay, 0.5 h. So we have the solution over here. That is the value of y at mid step. And after that, we use this value. Xi and yi to determine the slope at mid step. Okay. Xi is not 0.5 anymore. It should be y. Y is here. Y is here, and that's okay. And x and t should be here. Okay. T power 3. Okay. minus 1.5 y. Okay, that's already done, right? Okay, we got this value in fixed. Okay, because we have to use xy, this cell. Okay, and then the solution is what? Solution is yi. Okay, yi plus the slope at mid step. Okay, time h. Okay, time h. Then we got a solution like this. Okay, we do the same thing for time equal to 1. And until time equal to 2. Okay, we will obtain the solution like this. And the solution of midpoint, you see that it is the same. It is the same. You see that it produces the error at the final time step. At the final time step, the error is reached to 41%. That is not good enough. So what happens if we, so for smaller time step, for smaller time step, if I set up be 0.1, okay, so the solution is should be better. But finally, when time equal to 2, when t equal to 2, we found that the error is become 7.77%. And it's still not good enough, same as Huon and Euler. Okay, when the time, when we increase the time, the cumulative error produce a huge error in the final. Okay, so but from this concept, you see that we can adjust a little bit. We can adjust the term to try to forecast the solution of the ordinary differential equation based on Euler, Huon, and modify Euler or midpoint. We can adjust a little bit the increment function from initial slope to be average slope and then the slope at midpoint. Okay, and we found that when we adjust a little bit, the solution is better, but it's not good enough. Okay, then we will move to the Runge-Kutta method. Okay, I will overview you a little bit for Runge-Kutta method, and we will come back to Runge-Kutta method again by class activity next week. Okay, but I would like you to review the Runge-Kutta method from last year clip video first, in order to make you more understanding, and because we have the limit of time, next week it should be the last time that we will meet in this course, and then we will have the exam on 17 May. Okay, on Monday 17 May. Okay, and so next week is just the last week of this course. Okay, I try to conclude everything next week for the topic that we would like, that we should know. Okay, so for the midpoint, for the Euler, Huon, and midpoint, do you have any question?